For decades, astronomers looked at the Andromeda Galaxy through telescopes and thought they understood its scale. It appeared as a bright, elegant spiral lying across the deep darkness of the universe, a cosmic island similar to our own Milky Way. It was immense, yes, hundreds of thousands of light years across, but still comfortably within the range of what scientists expected from a typical spiral galaxy. But the truth, hidden beneath layers of faint light, invisible gas, and elusive cosmic structure, was far more astonishing and far more mysterious than anyone imagined. The journey toward measuring Andromeda's real size is a story of persistence, innovation, and a relentless pursuit of clarity in the vast chaos of space. When astronomers first began estimating the size of Andromeda, they relied on what they could directly see: the bright spiral disk, the shining star clusters, the glowing arms swirling gracefully around a central bulge. Telescopes captured these luminous regions with impressive detail, but what remained beyond that visible light was largely uncharted territory. The universe does not reveal its secrets easily. Much of a galaxy's true physical span lies not in the bright stars that cameras can detect, but in the faint, barely detectable halo surrounding it. A halo made of hot gas, ancient stellar debris, dark matter influences, and structures so diluted that early instruments simply weren't capable of recording them. For years, astronomers believed Andromeda's diameter was somewhere around 220,000 light years. This estimate came from the visible disk and the faint outer arms. It seemed reasonable, even impressive, but the universe has a way of humbling the limits of our assumptions. The more technology progressed, the more instruments became sensitive to load, density, gas, and subtle motions of stars, and the more scientists realized that they had only been looking at the tip of an incomprehensibly large structure. The real change began when astronomers started to combine multiple types of observations: optical light from telescopes, radio waves from giant ground-based receivers, ultraviolet measurements from space observatories, and precise star motion data from missions like the European Space Agency's Gaia spacecraft. Each tool revealed a different layer of Andromeda. Alone, none of these layers told the full story, but together they created a mosaic of clues that pointed toward an astonishing conclusion. Andromeda's true boundary extended far, far beyond what the human eye can perceive. Scientists realized that the faint halo surrounding Andromeda wasn't just a small sphere of gas. It was a massive, sprawling, diffuse cloud stretching so far outward that it nearly doubled Andromeda's estimated size, then tripled it, then eventually revealed something even more shocking. This halo, once thought to extend only a few 100,000 light years, was actually stretching across nearly half the distance that separates Andromeda from the Milky Way. If you could look at Andromeda not with your eyes, but with instruments capable of detecting extremely low density ionized gas, you would see not a tidy spiral glowing in darkness, but a colossal, nearly invisible bubble of matter enveloping it. This halo is made of material thrown out by ancient supernova explosions, the remnants of stars long dead, hot plasma drifting through space, and ethereal gas heated to temperatures so high that only ultraviolet and X-ray instruments can detect it. The more astronomers examined this halo, the more they realized its enormity. It reaches a staggering 3 to 1, 5 million light years in every direction. That means Andromeda is not 220,000 light years across, nor 300,000, nor even 500,000. When the halo is included, Andromeda's true size spans nearly 5 million light years. This measurement completely redefines what it means to understand the scale of a galaxy. Imagine standing on Earth and looking at the night sky. Andromeda appears as a faint smudge, something you could cover with your thumb if you held it out at arm's length. But that faint smudge is nothing more than a tiny, bright dot at the center of a far larger, invisible giant. If our eyes could see ionized gas instead of visible light, Andromeda wouldn't be a small patch in the sky. It would stretch across a vast portion of the heavens, overshadowing everything around it. It would appear as the largest object visible from Earth. This discovery didn't just change a number in a textbook, it changed our understanding of our cosmic neighborhood. It changed the map of the local universe, and it forced scientists to rethink the way galaxies interact, evolve, and influence each other across unimaginable distances. The realization that Andromeda is far larger than previously thought also revealed something even more profound. Its invisible halo overlaps with the halo of the Milky Way. That means the gravitational domains of our two galaxies are already touching. Even though their disks are separated by 5 million light years of space, their outer atmospheres have already begun to mingle. In a sense, the future collision between the Milky Way and Andromeda has already started, not with stars smashing into stars, but with halos exchanging heat, energy, and motion over millions of years. But before this insight, scientists struggled to measure the halo with accuracy. The gas is incredibly thin, so thin that a cubic meter of it contains fewer particles than the emptiest vacuum ever created on Earth. Detecting it is like trying to find a single grain of dust floating somewhere in a room the size of a continent. Yet somehow, astronomers succeeded. They examined how ultraviolet light from distant quasars was absorbed as it passed through the halo. They studied the way energetic particles interacted with the gas. They tracked the faint traces of metal ions produced by supernova billions of years ago. Slowly, painstakingly, the map of the halo began to emerge, and then came the breakthrough, the realization that Andromeda's halo was not only enormous but structured. It has layers, shells, filaments, and regions with varying temperature and density. The inner halo, closer to the galaxy's center, is hotter and denser. The outer halo spreads out into thin ghosts, like territory stretching almost halfway to our own galaxy. These layers tell the story of Andromeda's violent past collisions with satellite galaxies, bursts of star formation, periods of intense supernova activity, and interactions influenced by dark matter. Every piece of this story confirmed one essential truth: Andromeda's size was vastly underestimated. But there is another element that makes the discovery even more meaningful. It reveals the limitations of human perception. For centuries, we judged the universe based on what we could see. We assumed that the visible part of a galaxy represented its true boundary. But the universe doesn't operate on such simple rules. Much of its structure is invisible to our eyes. Dark matter, hot gas, diffuse ionized regions, and extended halos define the true architecture of galaxies, and these components cannot be seen with traditional observation. When the halo was finally mapped, scientists realized that Andromeda is not just slightly bigger than the Milky Way. It is likely far more massive and significantly more extended, making it one of the largest known structures in the local group. It is a gravitational titan, a cosmic heavyweight, existing right next door. This new understanding also raises deeper questions. How many other galaxies are much larger than we think? How many halos extend into regions we have never mapped? How much of the universe remains hidden simply because our eyes are not designed to see it? The realization that Andromeda's size eluded us for so long is a humbling reminder that the cosmos holds more secrets than we can ever imagine. It also adds a new layer of emotion to our relationship with the universe. When you look up at the night sky and see that faint, misty glow, you are not looking at something small or distant. You are looking at the core of a vast, sprawling entity whose full body stretches invisibly across the cosmos. You are looking at a giant who hides in plain sight. You are looking at a galaxy whose true form dwarfs our imagination and challenges our understanding of scale. And perhaps the most awe-inspiring part of all is this: despite the overwhelming vastness of its halo, despite being a galaxy so large that its boundaries touch our own, Andromeda is still just one of billions of galaxies scattered throughout the universe. And if even our closest neighbor can surprise us, what mysteries lie farther away? What silent giants float beyond our reach, waiting for the day our technology becomes powerful enough to reveal their true size? The story of measuring Andromeda's real dimensions is ultimately a story about humanity's relationship with the unknown. It is a testament to our curiosity, our refusal to accept simple answers, and our desire to understand the larger story of the universe. It reminds us that knowledge is not static. It evolves, grows, and expands just like galaxies themselves. Today, we can say with confidence that Andromeda spans nearly 2.5 million light years, making it one of the most dominant structures in our cosmic vicinity. But this measurement is more than a number. It is a revelation, one that reshapes our understanding of galactic boundaries, cosmic interactions, and the future of our own galaxy. And above all, it reminds us that the universe is far bigger, far more mysterious, and far more beautiful than our eyes can ever perceive. For most of human history, when we looked into the night sky, we believed that what we could see with our own eyes represented the true boundaries of the universe. The glowing stars, the faint smudge of the Andromeda Galaxy, the shimmering belt of the Milky Way, these visible lights shaped our entire understanding of the cosmos. But the universe is not a place defined by what is visible. It is shaped far more profoundly by what is hidden, what lies just beyond the reach of ordinary light. And nowhere is this more evident than in the discovery of Andromeda's enormous, almost supernatural halo, a structure so vast, so diffuse, and so ancient that it challenges everything we thought we knew about the scale of galaxies. When astronomers first began to suspect that galaxies had halos, they assumed these halos were relatively small atmospheres of scattered gas. Something modest, something that played a minor role in galactic evolution. They saw halos as faint leftovers, unimportant, unobtrusive, barely noticeable. But as telescopes improved, and as new wavelengths of light became observable, the truth began to change. Slowly, the idea of a halo evolved from a minor component into something colossal, complex, and absolutely essential. And in the case of Andromeda, the halo became the key to unlocking the galaxy's true size. To understand how astonishing this discovery is, imagine standing on Earth and looking at Andromeda through a basic telescope. You would see a bright oval disk, maybe a couple of degrees wide, with swirling arms that fade gradually into darkness. But the visible part of a galaxy is like the tip of an iceberg. Beneath the surface, beyond what eyes or even optical telescopes can detect, lies an enormous sphere of superheated gas and ancient stellar debris. This halo is not a faint decorative layer. It is the real border of a galaxy, and for Andromeda, that border is unimaginably large. The halo surrounding Andromeda is made of ionized gas, gas so hot that its atoms have been stripped of electrons. This gas is so thin that a cubic foot of it might contain only a few dozen particles. To the human eye, it is completely invisible. You could pass right through the densest part of the halo without ever noticing. And yet, this ghostly atmosphere holds clues to the galaxy's birth, its violent past, its ongoing evolution, and its future collision with the Milky Way. The breakthrough came when astronomers began using quasars, extremely bright, distant objects powered by supermassive black holes, to probe Andromeda's halo. When the light from a quasar passes through the halo, specific wavelengths get absorbed by the gas. By analyzing this light, scientists can determine what elements are present, how hot the gas is, and how far the halo extends. It's like using a flashlight to reveal invisible smoke in a dark room. The more quasars they examined, the clearer the shape of the halo became. What they discovered defied belief. The halo didn't end where they thought it did. It didn't taper off at a comfortable distance the way old models predicted. Instead, it stretched outward, far beyond expectations, reaching distances so vast that it effectively doubled, then tripled, then quadrupled previous estimates of Andromeda's size. This halo extended across a region so large that it reached more than halfway to the Milky Way. As the measurements improved, the numbers grew. 300,000 light years, 500,000, 800,000, a million. And then finally, after combining ultraviolet observations from the Hubble Space Telescope with star motion data from ESA Gaia spacecraft, astronomers confirmed that the halo reached up to 1, 3, or even 5 million light years in every direction. That means Andromeda's halo alone, just the halo, is nearly the size of the entire distance between our two galaxies. In other words, Andromeda's real size is not the bright spiral you see in images. It is a massive bubble of influence, gravity, and gas that spans nearly 5 million light years across. This bubble is not smooth or uniform. It has layers, like the rings inside a tree trunk, each ring telling a story about the galaxy's past. The inner regions are hotter, denser, and filled with heavy elements expelled by supernova explosions. The outer regions are colder, thinner, and composed of gas that has drifted for billions of years. These layers reveal ancient galactic mergers, periods of intense star formation, and times when Andromeda was shaped by violent forces. One of the most important discoveries about the halo is that it is chemically enriched. That means it contains elements like carbon, oxygen, silicon, and iron, materials forged inside stars and released during supernova explosions. These elements drift outward over billions of years, forming clouds of enriched gas that mix into the halo. This tells astronomers something crucial. Andromeda has been through multiple cycles of star birth and destruction. It has eaten smaller galaxies, it has absorbed their stars, their gas, their history, and each event left behind a signature preserved within the halo like fingerprints on cosmic glass. Another revelation was that the halo is not static. It moves, it rotates, it flows, it behaves almost like a fluid, influenced by the galaxy's dark matter halo. Dark matter, the invisible substance that makes up most of the universe, forms the gravitational skeleton of galaxies. The gas halo drapes itself around this skeleton, following its contours. By studying the gas halo, scientists can indirectly study the dark matter underlying Andromeda. This connection makes the halo one of the most valuable tools for understanding not just the size of the galaxy, but its overall mass and structure. The halo is also a kind of cosmic archive. It contains the ancient remains of dwarf galaxies that Andromeda has torn apart and absorbed. When these smaller galaxies were shredded by tidal forces, their stars were pulled into Andromeda, but their gas was thrown into the halo. The halo preserves these remnants like artifacts in a museum of cosmic evolution. One of the most fascinating aspects of the halo is that it changes our understanding of how Andromeda interacts with its environment. Because the halo is so large, it is already touching the halo of the Milky Way. This means that even though the disks of the two galaxies are still millions of light years apart, their outer atmospheres have already begun to mingle. The galaxies are sharing gas, exchanging energy, and subtly influencing each other's motion. The future collision between the Milky Way and Andromeda is not something that will begin in the distant future. It has already begun quietly, invisibly, through the merging of their halos. The discovery of Andromeda's halo also forces scientists to rethink what a galaxy actually is. Traditionally, galaxies were defined by their visible stars and their spiral or elliptical shapes. But the halo shows that a galaxy is much more than that. The true size and influence of a galaxy are hidden in these immense halos that cannot be seen with ordinary light. These halos contain most of the galaxy's baryonic matter, the ordinary matter made of atoms, and they dictate how galaxies evolve over time. Without understanding halos, we cannot understand galaxies. This shift in perspective is revolutionary. It means that the universe is filled with enormous, overlapping spheres of invisible gas. It means galaxies are not isolated islands, but interconnected structures, whose halos influence one another even across vast distances. It means the cosmic landscape is far more intricate and interconnected than anyone imagined, but the halo is not only important scientifically, it is also deeply poetic. It reminds us that the universe hides its most profound truths beneath layers of subtlety. The most important structures in the cosmos are not the bright, dramatic, eye-catching spirals that dominate astrophotography, but the soft, faint, nearly formless envelopes of gas that extend into the darkness. These halos represent the quiet, invisible architecture of the universe. Perhaps the most beautiful aspect of this discovery is how it reframes our relationship with the cosmos. When people look up at the night sky, they see stars shining like pinpoints of light. They see the glowing streak of the Milky Way. And if they are lucky, on a dark night, they see the faint oval glow of Andromeda, but what they cannot see is the enormous halo that stretches across the sky, embracing space silently. They cannot see how Andromeda's halo brushes against the halo of the Milky Way, forming an invisible bridge between galaxies. They cannot see how the universe is stitched together by these enormous, unseen structures. The discovery of Andromeda's halo reminds us that the universe is not made only of what we can observe. It is shaped far more profoundly by what lies beyond the reach of ordinary vision. It teaches us humility because it shows that even our closest galactic neighbor remained misunderstood for decades. It teaches us curiosity because each new discovery opens doors to deeper mysteries. And it teaches us wonder because the true structure of the universe is far more majestic than the glowing shapes we see in photographs. The halo also shows us the importance of multi-wavelength astronomy. No single telescope could have revealed this structure. It required ultraviolet observations, X-ray measurements, radio mapping, and precise star motion tracking. It required collaboration across continents and decades. It required technology that didn't exist even a century ago. This discovery is a reminder that human knowledge is cumulative, expanding with each new tool we create. The more we look, the more we see. The more we see, the more we understand. And the more we understand, the more the universe reveals its hidden grandeur. Today, when astronomers describe the Andromeda Galaxy, they no longer talk about a spiral of 220,000 light years. They talk about a colossal structure stretching nearly 5 million light years from end to end. They talk about a halo that is not just a border but a living, changing, cosmic ecosystem. They talk about a galaxy whose true size is defined not by its visible stars but by its hidden atmosphere, an atmosphere so large that it reshapes our understanding of the entire local group of galaxies. In the end, the discovery of Andromeda's enormous halo is more than a scientific achievement. It is a reminder that reality is often far bigger than our assumptions. It is a reminder that the universe is full of mysteries waiting quietly in the dark, revealed only when we develop the tools to perceive them. And it is a reminder that even the closest objects in the cosmos can surprise us with their scale and their complexity. When we look at Andromeda now, we do not see just a neighboring galaxy. We see a giant wrapped in a cloak of invisible gas. We see a structure so vast it nearly touches our own. We see proof that the cosmos holds more than we ever imagined, and that the journey of discovery is far from over. For decades, astronomers described the Milky Way and the Andromeda Galaxy as two colossal giants drifting toward each other across the silent sea of intergalactic space. They imagined the vast region between them as an empty void, a dark gulf separating these two spiraling titans. But the more scientists learned about the true nature of galaxies, their halos, their gravitational envelopes, their hidden regions of gas and dark matter, the clearer it became that this void was not empty at all. What once appeared as nothingness is actually an invisible battlefield of forces, interactions, and subtle exchanges. And now, with precise new measurements revealing the true size of Andromeda's enormous halo, scientists have uncovered a truth both profound and transformative. The Milky Way and Andromeda are not just approaching each other, they are already interacting. The idea that two galaxies could influence each other without physically touching may seem impossible at first, but in the language of the universe, distance does not mean separation. A galaxy is not merely its bright center or its visible arms. It is a sprawling system of stars, gas, dust, plasma, dark matter, and hot, ionized halo material extending hundreds of thousands of light years beyond what the eye can detect. These halos represent the true borders of galaxies, not the luminous spirals that telescopes photograph, but the vast, diffuse cocoons of ancient gas and dark matter that define their gravitational reach. When Andromeda's halo was finally mapped in detail, scientists discovered that it stretches an extraordinary distance, nearly 1.5 million light years in every direction. The Milky Way, too, has an enormous halo of similar size. When you place these halos side by side, something astonishing happens. They overlap. They interlock. They merge into a shared space of particles, heat, magnetic fields, and dark matter interactions. This means the two galaxies are not separate islands. Their outer atmospheres have already touched, fused, and begun exchanging material long before their bright disks collide billions of years from now. To understand how profound this is, imagine two great oceans on Earth slowly rising until they meet in the middle. The land masses remain far apart, perhaps hundreds of kilometers away, and yet their waters blend, currents form. Temperatures shift, marine life and nutrients drift across boundaries that once seemed fixed. The interaction begins not with the shores, but with the seas. In the same way, the interaction between the Milky Way and Andromeda began billions of years before their stars will meet. It began in the unseen waters of their halos. Scientists first suspected this invisible interaction when they discovered that the motion of gas clouds around the Milky Way did not follow expected patterns. Some clouds experienced slight pulls or distortions, tiny, almost imperceptible curves in their paths. At first, these deviations were dismissed as coincidences or effects from small satellite galaxies. But as data accumulated, patterns emerged. These distortions lined up in a way that pointed not toward an internal disturbance, but toward something massive and distant, something pulling on the Milky Way from the direction of Andromeda. This was the first quiet whisper of the interaction. Later, when astronomers used quasars to probe the space between the two galaxies, they found something even more compelling. Light from these extremely distant objects passed through not one halo, but a blend of two. The patterns of absorption lines, unique signatures left by intervening gases, showed that hydrogen, carbon, and oxygen ions in the intergalactic medium were being influenced by both galaxies simultaneously. In other words, the halos were already overlapping. There was no longer a clear dividing line between them. This discovery transformed our understanding of the cosmic neighborhood. The region between the Milky Way and Andromeda is not a barren void. It is a shared environment, a zone of early interaction where gas flows, magnetic fields twist together, and the gravitational pull of each galaxy influences the other. What we are witnessing is the opening chapter of a cosmic merger that will culminate billions of years from now. But this early interaction is not violent. It is subtle, gentle, and incredibly slow. The halos collide, not the stars. They intermingle like clouds, blending their gases in ways that cannot be detected by the naked eye. Yet this blending has real consequences. It affects the temperature of gas in intergalactic space. It alters the rate at which each galaxy loses material. It shapes the gravitational environment that their satellite galaxies move through. Even the motion of the Milky Way through space is slightly influenced by this halo interaction. Perhaps the most fascinating aspect is what this means for the future. The collision between the Milky Way and Andromeda has been predicted for decades, but the timeline and exact behavior of the merger have always remained uncertain. Now, with the discovery that the halos are already touching, scientists know that the early stages of the merger have quietly begun. The galaxies are gravitationally locked, their halos forming a bridge of influence between them. They cannot escape each other's pull. They are no longer independent giants drifting freely. They are partners in a slow-motion cosmic dance that will reshape the structure of the universe on a local scale. This dance is guided not only by gravity, but by the hidden forces within the halos. When halos overlap, they create pathways through which energy, particles, and even magnetic fields can travel. A halo is not empty space. It is filled with plasma, ions, and the echoes of ancient supernova explosions. These components carry heat and momentum. When the halos blend, this material begins to equalize. Hotter regions cool, colder regions warm. Flows of particles move across the boundary. The galaxies begin sharing a thermodynamic relationship long before their stars are close enough to interact. Another layer of interaction comes from dark matter, the mysterious, invisible substance that makes up most of the mass in the universe. Both the Milky Way and Andromeda have enormous dark matter halos, much larger than their normal matter halos. When these dark matter halos overlap, they create complex gravitational fields that affect everything inside them. The interaction of dark matter halos means the galaxies are no longer gravitationally isolated entities. They are linked by a shared gravitational envelope subtly shifting each other's motion and shaping the paths of nearby objects. This shared environment means that the Milky Way and Andromeda are no longer moving independently through space. They are falling toward each other in a very slow, graceful descent. The motion is not abrupt, it is not dramatic. It is a gradual, inevitable pull. Every million years brings them infinitesimally closer. Every gravitational tug, every exchange of halo material, every ripple of dark matter draws them into deeper connection. And this has been happening for millions of years already. The idea that galaxies interact long before they physically collide forces us to rethink galactic evolution. The Milky Way and Andromeda are often portrayed as two future combatants on a collision course, but the reality is far more poetic. Their halos act like extended hands reaching out across millions of light years. These hands meet long before the galaxies themselves embrace. And in that meeting, they have already begun shaping each other's future. Understanding this interaction also helps explain certain features within each galaxy. For example, some of the Milky Way's satellite galaxies behave strangely. They move along paths that seem influenced by a gravitational force stronger than what the Milky Way alone provides. Now, scientists realize that the gravitational pull of Andromeda contributes to these unusual motions. Small galaxies orbiting the Milky Way feel Andromeda's presence even from millions of light years away. The same is true in reverse. Andromeda's outermost satellite galaxies feel the Milky Way's gentle tug, subtly shaping their orbits. There is something profoundly beautiful about this interconnectedness. Galaxies that appear isolated when seen in photographs are, in reality, interconnected through invisible threads of gravity and gas. The universe is more woven together than we once believed, and the interaction between the Milky Way and Andromeda is a perfect example of this cosmic unity. The overlapping halos also influence the flow of cosmic rays, high-energy particles that travel through space. When halos collide, they create regions of turbulence and magnetic activity. These regions can accelerate particles, change their trajectories, and influence how they reach planets like Earth. Although this effect is incredibly subtle, it reminds us that even distant galactic interactions can have echoes that reach across unimaginable distances. The interaction also shapes the future star formation in both galaxies. Halos act as reservoirs of raw material for new stars. When halos blend, this material begins to redistribute. Some regions become richer in gas, potentially fueling future waves of star formation. Other regions lose material and become less active. Thus, the halos are not just atmospheres, they are engines of galactic evolution, influencing the creation of future stars billions of years in advance. One might wonder whether this interaction poses any risk to our solar system or our planet. The answer, fortunately, is no. The halo interaction is so diffuse and gentle that it has no direct effect on Earth. The material in the halos is so incredibly thin that even if the densest region passed through our solar system, not a single human would notice. The significance of the interaction lies in its vast scale and long-term consequences, not in any immediate danger. But the emotional impact of the discovery is powerful. To think that our galaxy is already touching another galaxy quietly, softly, invisibly, changes the way we see the universe. It reminds us that the boundaries we imagine are often illusions. It reminds us that we are part of a cosmic story already unfolding. And it reminds us that even the largest structures in the universe exist in a state of connection, influence, and relationship. In the end, The discovery that the Milky Way and Andromeda are already interacting is not just an astronomical revelation. It is a philosophical one. It tells us that separation is often an illusion, that even across distances measured in millions of light years, forces can reach out and connect. That the universe is not a collection of isolated islands, but a grand web of influence where everything affects everything else. And it teaches us that our own galaxy is part of a slow, magnificent dance, one that began billions of years ago and will continue billions of years into the future. The halos of the Milky Way and Andromeda are touching, they are blending, they are whispering across the void in a language written in gravity and gas. And in that quiet interaction, the future of both galaxies is being shaped at this very moment. The collision has not yet begun, but the connection has. The dance has already started. For decades, astronomers believed the timeline for the collision between the Milky Way and the Andromeda Galaxy was a distant, almost abstract event, something scheduled far beyond the lifespan of our Sun, far beyond any era humanity could possibly witness. The numbers were so large, so cosmic, that they almost felt comforting. 5 billion years, 4 billion years, a future so remote it might as well be myth. But new measurements of Andromeda's true size have changed the tone of that story. When scientists discovered that Andromeda's gaseous halo extends nearly 2 million light years into space, suddenly the narrative shifted. Two great galaxies are not drifting peacefully toward each other, they are already brushing shoulders, their edges mingling silently in the darkness. And this realization has reshaped our understanding of the timeline, not to make the collision closer in years, but to show that the process has already begun. Imagine two massive continents drifting across a global ocean. From high above, they appear separate, each rooted in its own region of the world. But deep below the water, beneath the surface where casual eyes can't see, their plates are pressing against each other, slowly but inevitably changing the shape of the world. This is exactly what is happening between the Milky Way and Andromeda. The visible stars are not touching. The spiral arms have not intertwined, but the halos, those invisible, ghost-like envelopes of superheated gas, dark matter, and cosmic dust, are already overlapping. And when halos overlap, galaxies begin interacting, gravity begins to tug more urgently, the intergalactic medium begins to flow differently. The early, silent chapters of a cosmic merger unfold long before any dramatic collision. To understand how this changes the timeline, we have to shift our perspective. A galaxy collision is not a single event. It is a long, slow choreography stretching billions of years. And every stage of that choreography has now moved slightly forward, not because the galaxies will collide sooner, but because the starting point has shifted backward in our understanding. For a long time, astronomers believed the dance would begin in 4 to 5 billion years, when the galaxies came close enough for their gravitational fields to seriously interact. But the discovery of Andromeda's enormous halo shows that gravitational interaction is already underway. The dance has started, we simply couldn't see the steps until now. Andromeda is moving toward the Milky Way at roughly 110 kilometers per second. That number hasn't changed. The predicted collision date, about 4 to 5 billion years from now, also hasn't changed in a dramatic way. But what has changed is the understanding of how the galaxies will behave during that approach. When scientists believed Andromeda was smaller, they imagined the first meaningful contact happening closer to the final approach. Now that we know its true size, that first contact moment is no longer in the future. It has already happened. When halos overlap, gravitational forces begin to subtly reshape the trajectories of stars, gas clouds, and even dark matter structures. Each galaxy begins to tug on the outskirts of the other, not enough to distort the shape of their disks yet, but enough to begin the earliest whispers of a gravitational conversation. Picture a massive ship moving through the ocean. Even when the hull is still far away, the waves it generates can reach you. They begin to influence your small boat long before the ship arrives. That unseen influence is what Andromeda's halo is now exerting on the Milky Way, and vice versa. The outer stars of both galaxies, the least tightly bound to their centers, may already be responding to this distant gravitational tension. The dark matter halos, those enormous, mysterious spheres that define most of each galaxy's mass, are beginning to sense each other. Gravity does not need visible contact, it only needs proximity. The new measurements suggest that the Andromeda Milky Way system is not two islands drifting in solitude, but a pair of massive structures already linked through an invisible bridge of energy and matter. This changes how astronomers model the future. Previously, simulations assumed the galaxies approached each other cleanly as isolated entities. Now models incorporate the early interaction of halos, meaning that the beginning of their gravitational entanglement is already underway. This can subtly influence the path the galaxies take as they spiral inward. It may cause earlier distortions in the far outer regions. It may alter the timing of smaller satellite galaxies caught between them, like the Triangulum Galaxy, which might join the merger or be flung outward depending on how these early interactions unfold. But perhaps the most profound shift is not in the timeline itself, but in the meaning of the timeline. Humanity is not waiting for a cosmic event to begin. We are living inside its earliest phase. Billions of years from now, alien astronomers in some distant civilization might look back and say that the first chapter of the Great Merger began now, with the detection of overlapping halos, but the discovery that the universe had already set its course long before any visible collision. The universe often begins its grandest events quietly, in whispers instead of roars. The future phases of the collision, though distant, now feel more grounded in reality. We can imagine them with greater clarity because we understand their foundations better. When the galaxies finally draw close enough, their shapes will distort. The neat spiral arms will stretch and twist like taffy. Stars will be thrown into long tidal streams, gas clouds will collide, compress, and ignite stellar nurseries on a scale our galaxy has never seen. But even this stage will unfold slowly, far too slowly for any creature to witness in real time. Stars separated by tens of thousands of light years do not crash into each other like cars on a highway. They pass through each other like ghosts, but their orbits change, their movements shift. The gravitational balance of the galaxy rewrites itself. What changes with the new understanding of Andromeda's size is that all of this is already being prepared. The halos overlap like the outer atmospheres of two approaching planets. They are sharing energy, exchanging particles, and blending gravitational fields. By the time the visible galaxies approach each other, much of the deeper merging will already have begun. This is like realizing that an eclipse does not start when the moon visibly touches the sun's edge. It starts long before, when gravitational and orbital alignments begin lining up with exquisite precision. Another way the timeline shifts is in what it tells us about cosmic evolution as a whole. Galaxy mergers are not rare events. In fact, they are the engines of galactic growth. The Milky Way itself is the product of dozens of ancient mergers. remnants of which can still be traced in streams of stars scattered across the sky. Andromeda too has devoured smaller galaxies. The halos of both galaxies contain the leftovers of these cosmic meals, chemical signatures, orphaned stars, dark matter fragments. When two massive galaxies merge, they reshape their entire region of the universe. And now that we know the merger has already begun on a halo level, we better understand how long such processes truly take. The timescales stretch not just across billions of years, but across the unobservable scaffolding that connects galaxies long before they visually collide. It's also important to understand what won't change. Earth will not survive to witness the merger, not because the collision is deadly, but because the Sun will evolve into a red giant long before the galaxies make visible contact. By the time the sky fills with Andromeda's glowing arms, Earth will no longer exist as we know it. But somewhere, perhaps orbiting another star, a distant descendant of humanity may look up and witness the breathtaking sight of two galaxies intertwining. For them, the night sky will not be a quiet ocean of distant points. It will be alive with motion, color, arcs of glowing stars stretching across thousands of light years. All of this, the drama, the beauty, the transformation, has its roots in what we have just discovered, the true size of Andromeda. The halo is the first ripple of a cosmic event that future civilizations will see as one of the defining spectacles of the universe. A galaxy is not just what we see, it is what we feel gravitationally, chemically, and energetically. And with Andromeda's halo reaching so far into space, the Milky Way is already feeling its presence. We are living inside the earliest phase of a cosmic dance that will reshape our entire corner of the universe billions of years from now. In the end, the new timeline does more than adjust numbers, it reshapes perspective. It tells us that cosmic events are not isolated, sudden moments. They are long processes, beginning quietly, invisibly, far earlier than we imagine. The discovery of Andromeda's true size is a reminder that the universe is never still. Even at this moment, forces beyond imagination are pulling, shaping, and sculpting the future of everything we know. And somewhere in the vast darkness between the two galaxies, the first threads of their eventual union are already woven, shimmering like a bridge made of time itself. For most of human history, when people looked at the night sky, they saw mystery. They saw stars that seemed eternal, unchanging, distant beyond imagination. The galaxies that fill our universe today are the end products of forces and events so ancient, so violent, so enormous, that our minds struggle to fully grasp them. But hidden within the vast, invisible halo surrounding the Andromeda Galaxy lies a kind of cosmic archive, a living record of what the universe was like billions of years ago. When scientists discovered the true scale of Andromeda's halo, they didn't just measure a boundary, they unlocked a window into our universe's earliest eras. This halo contains clues about how galaxies formed, how they grew, how they collided, and how the cosmic web shaped everything we see today. Imagine drifting through the outer edges of the Andromeda halo. There are no bright stars, no glowing arms, no swirling dust lanes. Instead, you float in a thin, hot fog of gas and ancient particles that were born in the earliest generations of stars. These particles have been drifting through space for billions of years, surviving supernova explosions, galactic mergers, gravitational upheavals, and cosmic storms. Every atom in this halo carries a story, where it came from, what it experienced, and what it helped shape. And because halo gas surrounds galaxies far beyond their visible boundaries, it acts like a memory field, storing the chemical signatures of events that happened long before planets like Earth even existed. One of the most important clues hidden in the halo is the presence of metals elements heavier than hydrogen and helium. The early universe had almost no metals at all. Everything beyond the simplest atoms was forged later inside the hearts of stars. When those stars exploded, they scattered these elements into surrounding space. Over billions of years, these elements became the building blocks of planets, moons, oceans, and life itself. By measuring the types and amounts of metals in Andromeda's halo, scientists can trace when certain generations of stars lived and died, revealing the timeline of Andromeda's ancient past. Some regions of the halo contain metals that could only have come from supernova explosions that occurred more than 10 billion years ago, before the Milky Way even finished forming. This means Andromeda saw massive waves of star formation early in its history, waves powerful enough to blow enriched gas far beyond the galaxy's visible arms. Other parts of the halo show signs of more recent events: bursts of star formation, collisions with dwarf galaxies, and tidal stripping, where smaller galaxies were torn apart and absorbed into Andromeda's vast structure. Each of these events left behind a chemical fingerprint, and by reading these fingerprints, we can reconstruct the ancient story of how galaxies evolved. But the halo does more than store chemical memories. It also reveals secrets about dark matter, the invisible substance that makes up most of the mass in the universe. The halo's shape, motion, and temperature are deeply influenced by dark matter. The gas floating through the halo is not just drifting randomly. It moves along unseen gravitational currents sculpted by a dark matter skeleton surrounding the galaxy. When scientists map the halo, they are essentially mapping the dark matter distribution itself, and dark matter is the key to understanding how galaxies form. Billions of years ago, before stars and galaxies existed, dark matter clumped together under its own gravity, forming enormous web-like structures across the universe. These structures became the scaffolding on which galaxies like Andromeda later grew. The halo still carries the imprint of those ancient structures. The way gas is distributed in the halo today preserves a memory of the earliest gravitational forces that shaped the universe. It is like looking at the foundations of a city built thousands of years ago and realizing that the modern streets still follow the layout of the original settlement. Another extraordinary clue in Andromeda's halo comes from stellar streams, long, ghostly trails of stars torn from smaller galaxies that fell into Andromeda long ago. Many of these stars now orbit in the halo, forming faint rivers of light that are almost impossible to see but easy to detect through their motion. These streams reveal how Andromeda grew, not peacefully, but through cosmic cannibalism. Every large galaxy in the universe has grown this way, by pulling in and consuming smaller ones. The halo is full of these remains. Some are recent, only a few billion years old. Others date back to the early universe. By studying the ages and orbits of these stars, scientists can reconstruct the history of Andromeda's violent past, how many galaxies it absorbed when these mergers happened, and how they reshaped the entire structure. There is also evidence in the halo of massive outflows, winds driven by supernova, or perhaps by a long, dead supermassive black hole eruption at Andromeda's core. These outflows pushed gas far into space, mixing it with material from other galaxies and contributing to the halo's enormous size. Some of this gas may have escaped completely, drifting into the intergalactic medium. Some may eventually fall back into Andromeda, fueling future generations of stars. This cycle of gas expulsion and accretion is one of the fundamental processes that shaped galaxies across cosmic time. One of the most fascinating discoveries is that the halo's outer regions contain gas with extremely low metal content, almost pristine material left over from the early universe. This gas has remained untouched for billions of years. It was never incorporated into stars, never enriched by supernova, never pulled into Andromeda's bright disk. It is like cosmic time capsule material, allowing scientists to study what the universe was made of shortly after the Big Bang. Finding such gas around a massive galaxy like Andromeda is rare and extremely valuable. It offers a glimpse into what the universe looked like when it was still young, still shaping its first galaxies, still cooling from the furnace of creation. The halo also helps explain how galaxies like Andromeda continue forming stars. For a galaxy to create new stars, it needs a steady supply of fresh gas. Much of that gas is believed to come from the halo. Over time, gravity slowly pulls the halo gas inward. As it flows toward the galaxy, it cools, condenses, and eventually forms the molecular clouds where stars are born. In this way, the halo acts like a cosmic reservoir, feeding the galaxy and prolonging its ability to form stars for billions of years. The Milky Way has a similar reservoir. This shared behavior hints at how common these enormous halos might be across the universe. Perhaps the most beautiful part of this discovery is the realization that halos connect galaxies to the larger universe. They are not isolated structures but part of the cosmic web, threads of gas stretched between galaxies, linking them across unimaginable distances. The Andromeda halo likely blends into the intergalactic medium, which in turn connects to the Milky Way's halo. In a sense, the halos of both galaxies are touching the larger universe, breathing with it, exchanging material with it. The universe is not a collection of separate objects, it is a single interconnected system, and Andromeda's halo helps reveal this grand unity. The halo also contains clues about one of the universe's greatest mysteries, how galaxies regulate themselves. Galaxies like Andromeda should have formed far more stars than they did. Something prevented them from burning through all their gas at once. The halo may hold the answer. The hot, diffuse gas in the halo acts like a pressure blanket, preventing cool gas from collapsing too quickly. This self-regulating mechanism may explain why galaxies evolve slowly instead of exploding in a single burst of star formation. It is one of the reasons galaxies like Andromeda survive for billions of years, maintaining stable disks, spiral arms, and habitable environments for planets. Every detail in the halo, every atom, every stream, every temperature fluctuation tells part of the story. It reveals when stars lived and died, when galaxies collided, when dark matter shaped the earliest structures, and how the universe evolved from chaos to order. The halo is like the fossil record of the cosmos, preserving moments that no telescope could ever have witnessed directly. Without halos, galaxies would be incomplete. Our understanding of the universe would be shallow. With them, we can see deeper into cosmic time than ever before. Andromeda's halo is not just a boundary, it is a history book, a vast, ancient, silent archive written in the language of atoms and gravity. And now that we finally measured its true size, we're reading that history with new eyes. We're discovering stories that stretch back to the dawn of time. We're learning how galaxies formed, how they survived, how they grew, and how they became the magnificent, sprawling islands of light we see today. The halo is the universe's memory. And by studying it, We are learning more about our own origins because the Milky Way has its own halo, carrying its own ancient stories, shaped by the same forces, filled with the same sacred remnants of creation. This is why measuring Andromeda's halo matters. It's not just a number, it's a revelation, a key that unlocks the deep history of everything. A reminder that the universe is ancient, alive, and endlessly evolving, and that every galaxy, no matter how bright or distant, carries within it the echoes of the universe that came before. For as long as humanity has looked into the night sky, we have relied on light to tell us the truth about the universe. We measured stars based on brightness. We defined galaxies based on what we could see. We traced cosmic distances by how far starlight traveled. And we built our understanding of the universe around the assumption that visibility equals reality. But the moment scientists finally measured the true size of the Andromeda Galaxy, something profound changed. For the first time, humanity was forced to confront how much of the universe remains hidden from our eyes, not just physically invisible, but conceptually invisible. The discovery that Andromeda stretches far beyond its glowing spiral arms, that its halo reaches millions of light years into the darkness, did more than redefine the galaxy's dimensions. It redefined our understanding of galaxies themselves, and with that, our understanding of our place in the cosmos. Andromeda is not what we thought it was. None of the galaxies are. The universe is deeper, larger, and far more complex than the comforting images we have grown accustomed to. The first shift comes from realizing just how much of a galaxy is invisible. For centuries, humans believed galaxies were islands of starlight, shining spirals, glowing disks, bright cores. Telescopes showed us glowing arcs filled with billions of suns, and we assumed those shapes represented the true boundaries. But the halo around Andromeda proved that the visible parts of a galaxy are only the beginning. Most of a galaxy's mass, structure, and history lies outside the regions that emit light. It's like seeing only the top of an iceberg and mistaking it for the entire thing. The luminous parts of Andromeda are merely the surface. The halo is the continent underneath, and once we recognize that, the idea of what a galaxy is begins to transform. This change forces us to confront a deeper truth. The universe is primarily composed of things we cannot see. More than 90% of Andromeda's mass is dark matter. The halo itself is mostly composed of invisible gas, invisible plasma, invisible particles that only reveal themselves through their gravitational behavior. It is as if the universe has been whispering to us for billions of years, telling us that light, beautiful, familiar, comforting light, is only one small piece of a much larger story. The real structure of the universe is built from shadows, not shine, and measuring Andromeda's true size makes this impossible to ignore. Another transformation comes from understanding how interconnected galaxies truly are. For generations, people imagined galaxies as separate islands floating through an empty sea. Each galaxy was thought to be self-contained, isolated, drifting alone across cosmic darkness. But Andromeda's halo shows that galaxies are not islands. They are part of a cosmic network. Its halo blends into the intergalactic medium, which blends into the Milky Way's halo, which blends into the vast web connecting all galaxies in space. The universe is not a collection of individual objects. It is a single, massive, interconnected structure, a cosmic ecosystem. The discovery of Andromeda's true size makes this impossible to deny. The Milky Way and Andromeda are already touching, already interacting, already sharing matter, already influencing each other's gravitational fields. This alone shifts how we see our place in the cosmos. We are not living in a solitary galaxy. We are part of a cosmic neighborhood, and our nearest neighbor has been closer both physically and gravitationally than we ever understood. This realization also changes how we tell the story of the universe. For generations, the narrative was simple. Galaxies form, they evolve, they shine, they eventually fade. But halos complicate that story. The halo contains remnants of everything a galaxy has been through: ancient collisions, long, dead stars, tidal disruptions, dark matter structures, cosmic winds. It is the memory of a galaxy, the diary it never meant to keep, and once we measure how big that diary really is, the story of the universe becomes deeper, longer, and more intricate. The universe is not just expanding in size, it is expanding in meaning. We begin to see galaxies not as simple objects, but as archives of cosmic history. Each one carries billions of years of memory. Each halo contains clues about how the universe grew and unfolded. Andromeda's halo is not just a border, it is a timeline stretching back to the dawn of the cosmos. Perhaps the most human shift comes from realizing how small we are, yet how incredibly privileged we are to measure something so massive. When we learn that Andromeda spans millions of light years, that its influence reaches deep into intergalactic space, that it interacts with the Milky Way even now, something humbling happens inside us. We gain perspective. We understand the fragility of our place in this immense, ancient universe. Earth becomes a tiny blue fragment orbiting a tiny star drifting inside a galaxy that is not even fully visible to our eyes. And yet, at the same time, the discovery elevates us. It reminds us that humanity has the power to measure things so enormous, so ancient, so far away, that they defy imagination. A species that evolved on a small planet, orbiting an ordinary star, developed tools capable of measuring the invisible boundaries of galaxies. This is not just science, it is a profound expression of what it means to be human, to seek, to question, to expand, to awaken. The way we think about cosmic collisions also changes. Before, the idea of the Milky Way and Andromeda colliding was a distant event, disconnected from the present. Something that would happen billions of years from now, long after we are gone, but now we realize the collision has already begun. The halos are overlapping, the gravitational fields are interacting, the first threads of the future merger are being woven right now. This doesn't make the galaxies collide sooner, but it changes what collision means. It is no longer a single catastrophic moment. It is a slow, majestic dance unfolding over eons, a cosmic evolution rather than a cosmic accident. And we are living inside its earliest stage. This makes the universe feel more alive, not a static backdrop, but a dynamic, constantly changing entity. Then there is the philosophical shift. When we believed Andromeda was smaller, the universe felt simpler. We saw galaxies as separate entities. We imagined space as mostly empty. We defined size only by what we could see. But now, with halos like Andromeda's stretching across intergalactic space, we must redefine all of those assumptions. Space is not empty, galaxies are not separate, and visibility does not equal truth. The universe becomes less like a collection of bright objects scattered across a void and more like a vast, interwoven fabric whose threads extend far beyond the luminous patches. In many ways, the invisible universe is the real universe, and now that we've measured Andromeda's true size, humanity must begin learning to see with more than just light. This discovery also changes how we imagine future astronomy. Telescopes of the past focused on visible shapes, spiral patterns, glowing cores, bright clusters. But the telescopes of the future will map invisible halos, dark matter distributions, cosmic filaments, and intergalactic currents. Astronomy will shift from studying light to studying structure, from observing brilliance to observing influence. Andromeda's halo becomes a blueprint for how future astronomers will explore the cosmos, not by looking only at what shines, but by tracing the forces that shape the darkness. Even our sense of cosmic danger changes when people hear collision. They imagine destruction, but knowing the halos are already interacting forces us to rethink what danger looks like. Galaxies collide gently, stars pass through each other without impact, space is too vast for physical crashes. A galaxy collision is not an explosion, it is a transformation. The halos demonstrate that the most important interactions happen invisibly, quietly, slowly, like two enormous clouds drifting through each other, gradually mixing, gradually reshaping their structures. This, too, changes our understanding of the cosmos. It teaches us that the universe's grand events are not violent catastrophes, they are slow evolutions that unfold with a strange, ancient grace. The discovery also changes our emotional relationship with the universe. Before, galaxies were distant, unreachable, mysterious. Now they feel closer. The idea that the halos are already touching makes the cosmos feel interconnected, intimate, alive. It gives us the sense that our galaxy is in conversation with another, that the universe is not silent. That gravity itself is a kind of cosmic dialogue written across millions of light years. When we finally measured how big Andromeda truly is, we did not just change a number, we changed how we feel about the universe. Most profoundly, this discovery shifts our understanding of ourselves. For centuries, humanity believed it lived in a well-defined, observable world. The sun, the moon, the planets, the stars, these were our boundaries. Then galaxies expanded our boundaries. Then the universe expanded them again, and now Andromeda's halo expands them once more. Every time we discover a larger structure, a deeper layer, a hidden dimension, we are reminded that the universe is always more than we think it is, and that we fragile, temporary beings are still capable of discovering its secrets. When we measured Andromeda's halo, we didn't just find its true size. We found humility, we found curiosity, we found connection, we found meaning. The universe became larger, stranger, and more beautiful all at once. And humanity, instead of shrinking in the face of cosmic immensity, grew in courage, grew in wonder, grew in its ability to ask even bigger questions. That is the real impact of this discovery. It is not about numbers or distances. It is about awakening. The Andromeda Galaxy is larger than we ever imagined, and because of that, so is our understanding of the cosmos, and so is our understanding of ourselves.